the thing is, how do you solve something like 2 to the x equals 7? Right? How do we solve something like 2 to the x equals 7? Because 7 is not a nice power of 2. Now, we should have an idea about what the power of x would be here. What kind of idea can we say is good, or what kind of, thing can we maybe say here with pretty, good certainty about this? It's got to be less than 3, but greater than what? 2, right? And is it going to be closer to 3 or closer to 2? Closer to 3, right? Okay? Because again, 2 to the third is 8. 7 is pretty close to 8. 2 to the second is 4. So 7 is between 4 and 8. Okay, so we know that the exponent's got to be between 2 and 3, probably closer to 3. Okay, but again, it's not going to be exact. So that means we know it's going to end up being like a decimal or something like that. Okay, so when we have an equation here, kind of an exponential form, this is what we would call like exponential form. Obviously because there's exponents and stuff, right? We have an equivalent form that we define using something called a logarithm. Okay. And we call that logarithmic form, right? And of course we read this as log base A of y equals x. Okay, that's kind of how we read that too. And you guys already knew that and stuff, but I'm going to say it anyway just because. Okay. So take a minute here, and don't take a minute, take a couple seconds, and just kind of like appreciate or, kind of examine what happens, right, when we convert from exponential form to logarithmic form, right? You'll notice when we talk about logarithms that it also has a base just like our exponent does, okay? And in fact, the base of the logarithm is the same as the base of the exponent, right? That word base is used in both cases here. This a is the base of the exponent, right? And it's log base a. So when we convert from here to here, the base stays the same. It just kind of changes its position, like where it is, right? That's still called a base. And then the x that is the exponent, right? It becomes like kind of like the thing that the logarithm is now equal to, and the y value here, this number, would go inside a logarithm. You take the logarithm of that thing. Okay. So, as a particular example here, if we want to evaluate, we can actually, you guys already know how to evaluate logarithms. Okay, so we'll just use the directions here: evaluate or simplify. Right, I'm going to start out real basic here with like log base 2, I don't know, let's say 16. Okay, and let's say we just want to evaluate this logarithm here, log base 2 of 16. Okay, so again, right now we're maybe feeling a little bit uncomfortable, right? Like, log base 2 of 16, what is it, Maybe some of you guys, you got it, no problem. What I would suggest you do, right, since logarithms we're not so familiar with, convert it back to exponential form, right? Let's just say that this thing that we're trying to simplify, let's just say it's equal to some value, we don't know what it is, we'll just say it's x. Right? Log base 2 of 16 is equal to some number, I don't know what it is, let's just say it's x. Okay. And now we can rewrite that using the logarithmic form there. Okay? So it'll be 2 to the x equals 16, right? 2 is the base of our exponent. The value that we had over here becomes the exponent. And then the y value that was inside switches over to the other side there, becomes 16. Okay? So you can kind of see how this changes around there. And now that we've kind of converted that into the exponential form, it's easy to solve, right? What does x got to be here? 2 to what power gives us 16? 4, right? It's got to be 4. So x is 4. Okay, so in other words then, log base 2 of 16 is 4. So when you are going to evaluate a logarithm, right, when you see something like log base 2 of 16, okay, what that really is asking to what power is 16 or equals 16? Okay. That's kind of like the work you're being asked to do when you're given a logarithm. Okay. Your base to what power to the answer, right, is 16. What's inside the logarithm there? Okay. So let's do a few other ones here. All right, again, we'll just evaluate a few more here. All right, so let's see here. Log base 3. Oh, let's not do 81. Let's do log base 3 of 27. Log base 3 of 27. Again, the question that's being asked here is 3 to what power is 27? Okay. 3 to what power is 27? And what's the answer to that? 3, right? A equals 3. N equals 3. Okay. Again, alternatively, right, if you're uncomfortable with that, you can take the log base 3 of 27. If you're uncomfortable with, like, that's like still really weird in your head, you can just take log base 3 of 27 and set it equal to some value x, right? We don't know it. Rewrite it in exponential form. 3 to the x equals 27, and okay, 3 to the x equals 3 to the third, so x must be 3, okay? And so you get the answer of 3 that way as well. Okay. Alright, let's try another one here. How about log base 5 of 1? So in other words, 5 to what power gives us 1 is equal to 1? 0, right? Anything to the 0 power is 1, except for 0, right? Except for 0. Anything to the 0 power is 1. Okay. How about four to what power gives us 2? Four to what power gives us 2? Yeah, see? Negative 1 would give us 1 over 4. We want 2, though. 2. So, yeah, Matt. 1/2 is right. Exactly right. Okay, right? If I rewrite this, right, as 4 to what power gives us 2, well, 4 to the 1/2 power, right? The square root of 4. Right? The square root of 4. 4 to the 1/2 is the square root of 4. So that gives us 2. Okay? All right. Very good. Let's try another one here. How about log base 10 of 1/100? So what power of 10 gives us 1/100? What's that? Negative 2. That's right. 10 to the negative 2 gives us negative, or 1/100. That's right. Okay. Alternatively, right, we can rewrite, so like that, you know, you can just like see it or know it kind of thing, but you can also, if you want, rewrite that 1/100th as 10 to the negative 2. Right? 1/100th is 10 to the negative 2. So 10 to what power gets us 10 to the negative 2? Well, it's got to be negative 2, right? I mean, that makes it much more obvious there, right? All right, so here, you guys try some. Same thing, evaluate. All right, so how about log base 2 of 64? Log base 100 of 10, and log base x of x to the 5th. And I'm going to specify that x is not equal to 0 in that case. Okay, so go ahead, take a second or two, and answer those. All right. Volunteers for the first one there. Log base 2 of 64. Volunteers. Yes, Devin. You got 6. So you're saying 2 to the 6th is 64? And yeah, that'd be right. Okay. That'd be right. Very good. All right. How about the next one? Log base 100 of 10. What's that one? Log base 100 of 10. Again, 100 to what power? 100 to what power gives us 10? Yep, Sean? What's that? 1/10? Well, let's see here. 10 to the, whoops, it's frozen. That doesn't help. There we go. 10 to the 1/10 gives us 100? What exponent do we need there? Well, 10, ooh, I got this backwards. I apologize. 100 to the 1/10. I apologize. There we go. That's what it should be. Okay. Sorry. 100 to what power gives us 10? 100 to what power gives us 10? So yeah, 100 to the 1/10. 100 times 1/10 would give us 10, but not 100 to the 1/10. What exponent? Sorry, what exponent there? So, right, 100 to the x equals 10. What goes there to make that true? Well, something we could do here, right, 100 is the same thing as 10 to the second. And that's 10 to the 1 there. Right? And when you have a power 2 raised to another power x, isn't it the same thing as saying 10 to the 2x equals 10 to the 1? I know I wrote that really small, but that's because I'm running out of space there. And if the bases are the same, and these two things are supposed to be equal, then their exponents must also be equal. So that means 2x equals 1, and so that means x has to equal what? 1/2. 1/2. Okay, 1/2. Okay, it's 1/2. 100 to the 1/2 power gives us 10. Less. Right. How about this next one? X to what power gives us x to the 5th? What should it be? Okay. X to what power gives us x to the 5th? Yeah, Caleb. It's 5. Yeah, it's not. Yeah. Yep, it's 5. That's right. Okay, again, x to what power gives us x to the 5th? That is the logarithm there. It's just got to be 5. Okay, that's all there is. Okay, that one was weird because it has the x thrown in, maybe. That's all. All right, questions on any of that? You're all just silent and no questions, though, huh? That's okay. All right, we'll move on. We'll move on. Okay, you can ask me questions later, I guess. All right. So, some special logarithms you'll run across. Log base 10, for example, of something is known as the common log. Okay, sometimes, instead of writing log base 10 of something, you'll just see log of something. Okay? So typically, if you see just plain old log by itself without a base written, you assume it's base 10. Alright? Now, that confused me when I went to college, and I had a professor that would use log and meant natural log. So just, which is the next logarithm we'll take a look at here. So just keep that in mind, right? But I think it's supposed to be log base 10 is the same as just when you see log by itself. That's, for example, the log button on your calculator. If you ever, wondered what that was, well, I'm sure you guys know because you've seen logarithms before now. But this log button on your calculator, if you press it, you'll notice there's no base, right? It just says log. That means it's log base 10. Okay, on your calculator, it's log base 10. Okay. So in other words, if I see something like log of 1,000. Okay, that's really saying log base 10 of 1,000. And 10 to what power gives us 1,000? To what power is equal to 1,000? To the 3, that's right. Okay. So if you see log 1,000, you get 3. In fact, if you type that into your calculator, log of 1,000, there it is, it's 3. Okay. Mind blown. You like log of 0.1, you get -1, because 10 to the -1 is 0.1. Okay. All right. Another special log is called the natural log. It is the logarithm with a base of the number e. Okay, we'll get a little bit more into like what e is, where it comes from. Okay, e though is a number, right? It's a transcendental number, right? So that means very special, right? It is like pi in that it shows up in a lot of different kind of applications. E, like pi, shows up a lot of times whenever you're talking about circles, right, and relationships among like arcs and things like that. E shows up a lot in the case of like continuous growth, right? So like for example, the growth of a population of like bacteria or something like that, or compounding interest when it comes to like money or you know, other types of, I guess, you know, any kind of continuous growth, really, continuous growth, okay? E shows up. And I think that's maybe why it's called, I'm wondering now if that's why it's called the natural log, because it has those, like, it kind of shows up in nature and things, too, in that growth idea, okay? By the way, E, okay, just like, again, pi, we know, is approximately 3.1415926, right? E is approximately 2.718. It is helpful to remember that, okay? And again, I'll show you kind of where that comes from a little bit later. But right now, we'll just start with that, okay? And so then log base e of x, okay, is really usually written as the natural log. So you see that written cursive L, cursive N, and then an x, okay? Or if you want, you can just write, you know, ln like that of x2, whatever, okay? So again, no base is given, but it's really a base e. Okay, and again, that's the natural log of x. And the reason why it's ln and not nl, right? Well, Mr. Witt, it's like logarithm natural, right? Well, that's because it's from the French. I guess a French mathematician was one that helped develop this, and it's like logarithm naturel or something like that. Okay, so I can't do French, sorry. All right, there are 3 basic properties of logarithms that we want to have down. All right. Property 1. Log base a of 1 is going to always equal what? 0, right? A to any power, or a to the 0 power has got to be 1. Okay. And of course, the stipulation, I mean, you know, you can say there that a is not equal to 0, of course, for all of these. I'll just put that here. A not equal to, actually, a greater than 0, I guess I'll say. No, that one's not a not equal to 0, I think, but then these other ones might be different. All right, well, anyway, there are stipulations there for that. Right. How about log base a of a? Why? Right? A to what power gives us just plain old a? Well, it's a to the 1. Log base a of a equals 1. And then third basic property here, log base a of a to the x. A to what power gives us a to the x? What should this always equal? X, yeah, whatever that x value is there. Log base a to the x. If you remember, right, that's what we saw some of these earlier problems that I had you guys try. For example, like, let's see here. Well, for example here, like the log base 2 of 64, right? That 64 could have been rewritten as 2 to the 6th, right? So log base 2 of 2 to the 6th, well, that just gives us 6, right? Log base x of x to the 5th, that was just 5, okay? Log base 100 of 10, that's a little bit trickier to see, but you know, you could rewrite 10 as 100 to the 1/2, and then I guess 100 of 100 to the 1/2 is just going to be 1/2. So, you know, same kind of idea there. It's a little bit weird with that one, though. All right, so those are the 3 basic properties. You'll be using those to help you out. Okay? All right. And then the last thing I want to do here is just look at what a graph of a logarithm looks like. Okay? So what a graph of a logarithm looks like. Okay? So, let's take a look at the graph of log base 3 to the x. Sorry, not base 3 to the x, base 3 of x. Okay, log base 3 of x. And so we'll make a little table here to kind of help ourselves out some. Okay. And so let's see here. Let's try. Well, so we want to be careful. We want to be kind of selective here about some of the x values we pick. For example, let's think about -2. Okay, let's think about -2. So in other words, for this y value here, I would need to do log base 3 of -2 equals, you know, some number over here, and that would be my y value, right? I'll put my y right there, I guess. Okay, log base 3 of -2 equals y, right? Which means if I rewrite that in exponential form, I'll have 3 to the y equals -2. Is there any power that I can raise 3 to that power and get a -2? Is it possible to take a positive number, raise it to some power, and end up with a negative answer? The answer is no, right? Impossible. And so we don't want to use any negative x values, right? Okay. What about 0, though? What about 0? So in other words, log base 3 of 0. Well, now we're saying 3 to some exponent, right? If I rewrite this in exponential form, 3 to some exponent is going to equal 0. Is it possible to take 3 to some power and get 0? Yeah, no. So again, 0 is a no-go in this case, right? All right. Well, goodness, let's try 1. All right. And now we finally have something, right? 3 to what power gives us 1? 0, right? 3 to the 0 gives us 1. So log base 3 of 1 is 0. Okay, log base 3 of 1 is 0. Okay, and then we can continue on here. So again, I could pick, like, I could put 2 here as well, but then I'm going to have a problem because 2 is not a power of 3. So we want to pick like powers of 3. So let's say like maybe 3. And we can do like 9. And maybe, I don't know, I guess I'll do one more here, like 27. Okay. So again, log base 3 of 3. What will that equal? 3 to what power gives us 3? 1, right? Okay. And then log base 3 of 9, 2, and then log base 3 of 27 will be 3, right? And so we get 1, 2, and then 3 there. All right, and so let's take a look at the graph of this thing. So again, it's not possible for me to have any negative. I can't take, you know, the negative stuff didn't work, the 0 didn't work. So I'm going to focus really on the first quadrant here. It looks like. And let's see, how am I going to count this? Maybe I'll count by like 5s or something like that. 5, 10, 15, 20, 25, 30. Okay, and then maybe I'll count by 1s here. So 1, 2, 3. Like that. So we'll plot some points here, right? 1, 0. All right, so 1, 0. So here's like, I don't know, I'll put it like right here maybe. Okay, x value of 1, y value of 0. Next we have is 3, 1. So again, 3 is going to be closer to 5, but now up this much. All right, 9, 2. Okay, and then 27. So we'll say 26, 27 there, and then 3. So it looks something like that. Now, you guys don't know how to graph this on your calculator yet, probably, but I'm going to do it and just show you what it looks like. Okay? So if we graph this, log base 3 of x on our graphing calculators, okay, there's the graph. And if you look, our graph doesn't quite match up to what's on the graphing calculator there. In fact, the graph yields some negative y values, right? It goes below the x-axis. Right, using these numbers that we selected, we only got this positive part of the graph, but there are negative parts to it. It does go below the x-axis there. How does that happen? Well, there are other powers of 3 besides 3, 9, and 27. For example, 1/3. What power of 3 is 1/3? It's 3 to the what? -1, right? We can also say like 1/9. Log base 3 of 1/9, or in other words, 3 to what power gives us 1/9? -2. Okay, so we can go negative here, but it's going to be obviously like really teeny tiny. So what is, excuse me, what is the domain, what do we think, what does it look like the domain of this function will be? From what to what? 0 to infinity. Do we include the 0 or exclude the 0? Exclude, right? We can't equal 0, right? We saw that earlier. We can't equal 0. So in fact, that's right, yes. What's the range look like here? It's going to be negative infinity to infinity. Okay, this continues to grow without bound. It's not going to have some sort of like limit or anything like that. It keeps going without bound. Okay. So you won't ever take the logarithm of a negative number, right? But a logarithm of some numbers can yield a negative value. Okay? So you'll never take the logarithm of a negative number or of 0. Right? But sometimes a logarithm will yield a negative number or yield a value of 0. Okay? So there's that. Okay. You'll notice one other thing here, or some other things here I want to talk about, right? We could say that we have like a vertical asymptote at x equals 0. I have an asymptote that our function is approaching. We do also have an x-intercept as well, right? Crosses here at 1, 0. Okay. But of course, there will be no y-intercept because the domain only goes to 0, but not including the 0. So, I'm going to stop here, and at this point, I'm going to let you guys get started on the assignment. Okay, so we get some practice with this, because I think that's what we just really need, okay, to get more comfortable with this. So, we will do that here. Let me get started. So, first thing I have for you, it's going to be like two-parters. I have a paper here that's just got some logarithm practice for you that I want you to do without a calculator. Okay. want you to do this without a calculator, just get some practice down and start figuring things out. And then I also have a little bit of bookwork too. If you want to do the bookwork on the back of the paper, that's fine. And once I get all these out, I'll start coming around and getting your, giving you your grades, your grades for your tests, and then also get your group stuff. What's that? You just have a good Friday, guys. But what if your test grade would make you have a better Friday? Okay. Well, the problem is, if grades only want to know it's good, and I don't know that you know that, there's no win. Grades didn't give you permission to do that. All right, so then the book assignment. So the homework is the log worksheet and page 234, numbers 37 and 39. Okay? So you have these two problems in addition to the worksheet. All right, let me get this all squared away here. Yes.
Should I publish the test during the session?
So if you want, I can have you do it right now. Is that okay?
Yeah.
All right, let's have you do that. 1 second, though. Let me get this. No, I don't want to pass it back because some people have to finish. But thank you.